multiple Chromes, whatever. There are a lot of people accessing Canvas at any given time with different browsers. So it looks more like this, and there wouldn't be just two. There would be like lots and lots of browsers connected to the web server. And then the web server still really only has, at least in this diagram, has one connection to one database server. So what does this mean for things like checking out a book from the library? Let's say two people on different machines with different web browsers, or even the same web browser, doesn't matter, two clients, try to check out the same book at the same time. So the web server is basically going to spawn two threads, one for each client, or maybe two processes even. And they're both going to start running this insert into command. And then that insert command takes some finite amount of time. So I've got this like clock picture here. Like it's not going to happen instantly. If the threads associated with both clients are trying to do this at the same time, you essentially have a race. Okay, so remember the checked out table has a primary key, which is serial number of the book. So if they're trying to check out the same book at the same time, there's a race. Like you cannot have two of the same serial number in that table. So what happens? Does it insert two rows with the same primary key? Does it like does one of them actually just corrupt the database because they're both doing some things to the internals of the database at the same time? Turns out the answer is no. The database system will automatically protect against this kind of race. So back to here, one of these insert commands will succeed, and the other will be a primary key violation, since the book would already have been checked out. Okay, so that's good. We don't have to manually worry about things like that. But that is a very simple example. There's a single SQL statement happening here. So the reason this works is because it's not just magic. It's not just some fundamental aspect of, since we're using a database instead of some other software. The reason this works is because every operation you do by default is done in something called a transaction. And essentially what that means is that it's guaranteed to either completely fail or completely succeed. So think about a race condition in the context of just a multi-threaded program, not a database. You could have one thread, write some, read some value, write some value to some piece of memory, and then another thread could then go and overwrite its value. Having read the same original old value, you have a race condition and the data gets corrupted. The problem there is that both threads were allowed to kind of just do their work, even though one of them was interrupted and it kind of partially succeeded. One of them partially succeeds, the other one either fully or partially succeeds. The idea behind a transaction is it's either going to totally happen or not happen at all. You cannot get like halfway through it and then just leave it kind of in that halfway state. And so not only do they have the completely fail or completely succeed property, they also have this property that they will not interfere with other transactions. And all of this stuff about transactions, the design principle behind a transaction is this acronym ACID. So atomic, consistent, isolation, and durability. The atomic part is the completely fail or completely succeed part. The consistent part in the context of a database is any transaction that starts on a valid database will leave the database in a valid state. So a transaction cannot violate primary key constraints, foreign key constraints, cascade rules, everything like that. Isolation is just the non-interference part. if two transactions are kind of happening simultaneously or concurrently, they can appear to each other as though they are isolated and they have their own little world. They'll do their own things and not really worry about the other one. And then durability means if the transaction completes, then the database is updated. So unlike in, say you make a write call in just some program. You write some data to a file, and then your program immediately crashes. And you restart your computer, and the data is not actually there in the file. Because the write kind of tricks you and just says, yeah, you wrote some data, but I'll just keep it in memory for now and not actually commit it to the file. That's a durability problem, and databases don't do that. If a transaction completes, the data is permanent. Okay, so all of this stuff, this ACID stuff, relates to transactions and the model behind how you interact with the database. It turns out everything we've been doing with all these commands we've been running, they are actually running inside of a transaction, and they have this ACID property. Sort of question? Consistency. So if I insert, say I have two tables and one of them has a primary key into the other, and it has something like on delete restrict. So consistency means that on delete rule, restriction, will always be applied. It's an invariant. It is true at all times. I cannot delete a row from table A if a corresponding row exists in table B, if there's a foreign key restrict property on it. Or another example is just you cannot have two of the same primary key values in some table. You could imagine easily being able to break that if running an SQL command is, it takes some finite amount of time. It's a multi-step process. Maybe you add some violating key to a table before checking whether it would violate, and then the server crashes. You end up with an inconsistent database.
So even if you're trying to insert a row that depends on one key in another table, at the same time as somebody else at that exact moment could delete the other one or the other of those will happen, but not both.
Right. So if one table is trying to insert a row that depends on a foreign key, and another session is trying to delete some row related to these foreign keys, whatever happens, it'll end up in a consistent state, but it still may not be what you intended to happen. Okay. And it also kind of depends on how long the transaction is. We'll kind of get to that more. So, any good DBMS will provide ACID transactions, including the one that we use. And so, like I said, it turns out even with just a normal, simple, single insert SQL command like this, that's actually done as a transaction. Okay. So let's expand this a little bit. Let's say we're dealing with bank accounts, and there's like a transfer money from account X to account Y. So this is subtract money from one account, add money to the other account. So you might do this with, say, two SQL commands. Update balance equals balance minus 100 for account X. Update balance equals plus 100 for account Y. Okay? So each of these is a single operation, and each of them will completely succeed or completely fail. So you're going to end up with, neither of these two operations will leave the database in an inconsistent state. But let's say right here, in between these two, after subtracting money and before adding money, the server crashes. Okay, so this operation never actually runs. The first operation does run and subtracts money from one person but doesn't add it to another, so the money is just gone. So this kind of is kind of counter to what I was saying, where everything either completely succeeds or completely fails. But this is two operations. Each of them individually will completely succeed or fail. So what we need is something like this whole thing to be one operation. And you could maybe rewrite your SQL commands so that it does all of this in one operation. But you can't rely on always being able to do everything in a single command. So turns out we can actually, and then so let's say the server crashes here. Even if it kind of got partway through and started updating one account, if the server crashes there, if this whole thing is somehow treated as one operation, then and if we have ACID, then the whole thing will fail. And whatever it partially did will either never have really happened in the first place or be undone in some way. So we can do that. We can actually manually increase the scope of a transaction. Instead of it just being one SQL command, I can say start transaction and then do any number of commands and then commit. So these are the actual SQL keywords, start transaction and commit. Anything that happens in there is kind of working in its own little like sandbox type thing. And if the server crashes before the commit, then it's as if nothing in there ever even happened.
Is that what Link is doing in the background when it requires us to save, say X?
So is that what Link is doing when it requires to save what?
When it requires us to save reads and X?
Right, so whenever you do save changes in Link, that little save changes C# command is actually running everything it does inside of a transaction. Yep. So it's not going to like save a few of the things and then crash. It's going to, if it does do that, then the server will detect it and the server will undo anything that was partially done.
So I never had to write start transaction and commit manually.
Right, so you don't have to write start transaction and commit in Link because save changes automatically does all of its stuff inside a transaction.
But even in SQL?
In SQL, yeah, you don't. If you never write start and commit manually, then your single operations like this are single transactions. So this first update would be one transaction, second update would be another transaction. And something bad can happen in between and leave the database is still in a consistent state as far as the relational model, but as far as like your bank account, you've lost money.
When we save changes, how do we know that that succeeded? Or does Link?
When you save changes, how do you know it succeeded? The server will return when the transaction is complete, and then C# will either return something or throw an exception or not throw an exception. That's how you know what happened. So that durability part of ACID. If the server ever replies with this transaction is done, that means that it is permanent on the disk in the database server. Okay. So if anything goes wrong there, it's server crashing, client crashing, one of these commands fails or does something illegal, the entire transaction will just fail, and it's as if nothing ever happened. We can manually also roll back a transaction. If at any point during the transaction we decide that we're done or we can't complete it for whatever reason, we just run the rollback command, and then everything that happened up until the start is undone, as if it never happened. And so whether or not it's actually undone versus did it even ever happen in the first place kind of depends on implementation details. It's sometimes a transaction will actually change certain things and then the rollback will undo them. Sometimes it's kind of operating in its own sandbox, and on a rollback, then it just throws the sandbox away and nothing ever happened.
So is it basically the analog to commit, except, or saying like this is the end of the command, but we don't want to commit.
Right, exactly. So it's similar to commit in that we're saying this is the end of a transaction, except instead of making it permanent, we throw it all away. Yep. Okay. So this mostly, well, transactions do make sense inside of a single session where you want some complex operation to either fully succeed or fully fail. That has nothing to do with concurrency or threading or anything like that. But transactions also have interesting interactions when there are two sessions active. So, if I'm running some SQL commands and someone else is running some SQL commands, our transactions can kind of cooperate and interfere with each other. So, by default, there are ways you can change this, but by default, the changes made inside of a transaction are only visible inside of that transaction until you commit. So let's say over here in session 1, I start a transaction, I do some insert or delete or any kind of change. Then I can do a select and it will show me those changes, even though they're not actually permanent on the server yet. Over here in session 2, if I do some select related to whatever data was changed in the blue session, it will still see the old data, as if the insert or delete has not happened yet. Then, when session 1 commits, if I select again in session 2, now it will see the new data. Or if session 1 were to roll back instead, then this second select in session 2 would still see the old data. Okay, so this rollback thing, it makes, conceptually it makes sense. All it's doing is undoing a transaction. Turns out it's not usually that useful to manually roll back, to explicitly roll back, unless you're just kind of messing around inside of a terminal, maybe doing some testing or something like that. If a transaction needs to be rolled back, it's usually just going to be automatically detected by the system and rolled back. You're usually just going to assume, I'm going to start my transaction, do whatever I need to do, try to commit. If anything goes wrong, it will be automatically rolled back.
Is there a way to use the fact that you can roll back to do unit testing with an
Right, yeah, so good question. So can you use rollback to do unit testing? Yes. You can take an existing database, start a transaction, mess with it a bunch, then roll back. And that's kind of a safe way of making sure you don't change anything. Sometimes when a new database admin or trainee or something starts working on a new big database, they can only do anything inside of a transaction and they cannot commit, they can only roll back. It's kind of a safe way of letting them play around with it. Yeah. Okay, so rollback is more useful when it's automatically done. Like if your insert interferes with some other transaction, like some other transaction already put that primary key in there, or if your connection is interrupted or the server crashes or whatever. Yeah.
Is rollback like a try catch in SQL?
Is rollback like a try catch? Kind of the same idea where you have this big scope, and if anything goes wrong in it, then you jump and do something else. But not the same in that a rollback is actually going to undo everything that was done. A try catch, if you catch an exception, it's not going to undo anything that happened inside of the try. Okay. So let's play around with some transactions. I have 2 sessions open here. So there's one on the bottom and one on the top. It'll be a little hard to fit them both on the screen, but we'll try. So I'm in my Sandbox database. That doesn't mean Sandbox in terms of like a transaction, but this is just, we have a super simple table in here, a couple actually. Simple 1 and simple 2. Simple just has a single int column. So all we're going to do is just try inserting, selecting some things from that column within 2 different sessions. Okay. So if I start a transaction over here in session 1, okay, now I can do insert into simple values 1. So I'll just insert the integer 1 into that int column. Oh, I already had some stuff in there. Let's do 2. Okay. Now over here in my other terminal, in my other session, select star from simple. So the 1 was already in there, and the 2 I just inserted in my other session. So session A, I did an insert. Session B cannot see it. Select star from simple over here inside the transaction. Now I can see the 2. But that's kind of fake at the moment. For now, it's not really there. I can roll back. And then if I select star from simple, it's gone. And nothing ever happened in the other session. Okay. Let's start another transaction. And start a transaction in both. So I have 2 transactions going now. Just to start out, let's select star from simple. So there's the 1. There's the 1. So notice I have both of these are running inside of a transaction, and they were both able to run a select command. So it's very important not to think of a transaction as a lock or a mutex. Both of them were able to enter their transaction and do something. Okay, if I insert into, so insert a 2 into the table, do a select over here, nothing is there. Okay. What if I try to insert another 2? So now it turns out this insert command is just waiting. It's kind of just, it's hung. It's blocked. If I roll back over here, now this one suddenly succeeds. So there is some communication going on between these 2 transactions, some kind of synchronization, but not like a mutex. It turns out it automatically detects when it needs to synchronize, when it doesn't, and figures out when things would interfere or not. Yeah.
So does transaction B need to wait for transaction A to finish before it can start? If they're modifying the
Does it mean that the transaction A needs to finish before transaction B can start? No, it's more related to individual commands within the transaction. So the synchronization here was not related to the whole transaction. It was related to the fact that they were both trying to insert a conflicting row.
Was it because you were trying to insert a row into simple in each of them, or because you were trying to insert the same row in simple?
So was it because I was trying to insert a row into simple, or because I was trying to insert the same row? So let me roll back that one. So just make sure they're both in the same state now. so back to no transactions running. Let's start a transaction again in both. And then over here, I will insert 2. Over here, I will insert 3. And no copy. So it's actually very smart in terms of like what can proceed right now and what can't. A lot less restrictive than a mutex in that regard, and thus potentially a lot higher performance. Roll back that. Roll back that. Okay, one other question first.
So it seems like you could get into like a deadlock situation if you had transactions, a lot of things over here, a lot over here.
Yes.
You're waiting on me to finish, but you're waiting on me to finish.
Yes, you can definitely get into a deadlock situation, and MySQL is very good at detecting deadlock, and will, in fact, we'll just abort one of the transactions. So I'll show you a situation here where a transaction is aborted, not due to deadlock, but here's the one other thing I wanted to show. Let's start 2 transactions. Go back to, they're both going to try to insert 2. So this one has to wait. And what I did last time was I did rollback in this one, but if I commit in this one says OK. This one says fail. So depending on, if the one that committed is the one that kind of gets precedence, and the other one that's waiting on that locked row, the system will automatically just kill it. And my transaction is done now. It's been automatically rolled back because of the error. Okay. So back to this question of many clients interacting with one web server. Maybe transactions can kind of help here, but let's look at it. So let's say instead of, so the operation we were doing was checking out a book. But let's add to this a little bit. Let's say that when checking out a book, you actually have to leave one copy for the library, at least one copy, so that people can come in and like read it in person or whatever. So you would do something like figure out the count. How many copies does the library have? How many are available? Then just do some C# or even SQL logic to figure out if that count is greater than 1. If it is, then you can check the book out. Otherwise, you have to stop. Even though there is one copy, you can't go down to 0. So basically, the difference here is this now requires 2 commands: one select and one insert. By default, these are one operation. So each of these will be run in its own transaction, and it's not much different than regular serial control flow here. Select if count greater than 1, insert. But if 2 clients are interacting with the web server at the same time, you could imagine that both of them will get past this if statement at the same time, even when there's only 2 books left, and they will allow them both to check out the book. So I actually have my library web server updated to do that. So here's checkout book. Instead of just insert into checked out, it's actually a little more complicated now. I have to figure out if the number of books available will leave 1 for the library. So turns out this is actually kind of an interesting query because all we're given is a serial number. We have to kind of work backwards from there to figure out the other serials associated with that book. So we have to go like, back and then forward to find all the same serials. So I have a few queries in here. Don't worry about them too much. This is the important part right here. copies query.count minus checked out query.count. So how many total copies does the library have minus how many of them are checked out? That's how many are available. And the rule is we have to leave one for the library, so I'm checking to make sure that if available is less than or 1, then I just say false. You cannot check out the book. Okay. So let me just show you that running in the web server with this new restriction. Okay, we will just log in as someone. And we get the main page. So let's look at Harry Potter. I have 2 copies available. I could check out either one of them, but the system's going to require that we leave one for the library. So if I check out that one, okay, checked it out. If I try to check out that one, it'll still refresh the page, but didn't actually let me check it out. Okay. Let me reset that. I'll just open up one of my terminals here. And I'm just going to delete from checked out. Let's just verify. Okay, so both are now available. It's faster to do it through the command line than going and clicking on return book. Okay, good. So that appears to work. It didn't let me check out the very last copy. However, let's say right here, after figuring out how many copies of the book are available, let's say some other client running and gets to this point. So 2 parallel clients. All they've done up to this point are select commands. So they both select the same stuff, and they both get the same value for available. There's no way I could actually click fast enough in 2 clients to actually show that. So I'm going to just slow things down. So let's just put in a 5-second sleep right there. And then I'll actually run this in 2 clients. So I'm going to have one browser here. I'll try to split them equally. Let's wait till the first one finishes loading so we know the web server is up. Okay, I'm just going to copy that URL. Okay, so we have 2 clients running now. So I'll try to check out Harry Potter serial 1001 over here and 1002 in the other client. And then we'll have to wait 5 seconds. So it looks a little weird, but this is definitely a problem. It let me check out both copies. Why is it showing up this way in the other one? That's just because it refreshed before the other checkout happens. If I manually refresh this one, now they both show that somehow somebody was able to check out the last copy of Harry Potter, even though we're explicitly forbidding that right here, because it's a race condition. Both of them were able to get through the part where they read the number of copies available before either one of them had changed the number of copies available. It's a classic read, modify, write race condition where two of them read the old value before one of them wrote a new value. Okay. So let's try to fix it. Let's wrap this whole thing in a transaction. So the way we do that in LINQ, unfortunately, we can't just do something like start transaction. You have to do it through C# objects and mechanisms. I've got it just kind of down here, ready to go. Instead of copying it all, I will just kind of show you quickly. Okay, so these 4 lines, this is how we start a transaction. First thing we have to do is, so DB is that library context thing that we've been dealing with this whole time. We have to manually and explicitly open a connection using that context, because otherwise the connection is not actually open until I try to run some LINQ query. But you have to have an open connection before you can start a transaction. I make a transaction using database.getConnection.begin transaction. So that's just giving me an object, a transaction object. Now here's something that we haven't really addressed yet. Auto transactions enabled equals false. We'll talk about that in a second. And then I just say database.use that transaction. All of that is kind of equivalent to start transaction. So this auto transaction enabled false part, I have to do that because otherwise this database.saveChanges here will try to run inside of its own transaction, and they kind of interfere with each other. So I have to manually turn off auto transactions since I am explicitly starting my own. That's just so that they don't interfere. Okay, so I've started a transaction. If we get to this failure point where we've decided we can't check out the last book, then I just want to roll back before returning. I don't have to do that. It'll automatically roll back as soon as the transaction goes out of scope by this return statement, but it's always better to be explicit. So I'm going to roll back there, and then I'm going to commit after my save changes. Save changes normally automatically does a commit, but I disabled it because I want my own transaction. Okay. Let me reset the database again, so nothing is checked out. And then let's try it with 2 clients again. Oh, I have to close all instances of Chrome. Okay, so let me get another browser so we can do the simultaneous clients. Okay, so both copies of Harry Potter are back. I manually reset them. Let's try it again. Check out this one and that one. And we get exactly the same thing. It still somehow let me check out both Harry Potters if I refresh this page it shows the same thing. So the transaction did not solve the problem. Let's take our short break now and figure out why. Start a transaction in session 2. I can select, I'll just do count. Okay, that works. That works. That is essentially the problem right there. A transaction is not a lock. It's not, one session running a transaction does not prevent another session from running a transaction. It only synchronizes when things start to interfere. Select, by default, is not considered to interfere. So this doesn't work. Just wrapping this around start, transaction, and commit is not the same thing as lock and unlock. Transaction is not a mutex, even though it kind of seems sort of along the same lines. A mutex has lock and unlock. A transaction has, it's not just that they're different names. They are well named and they mean very different things. Start and then either rollback or commit. So the fact that it even has two different ways of ending a transaction means it's very different from a mutex. A mutex, the entire purpose is mutual exclusion, preventing two things or more from doing the same thing at the same time. A transaction has no such requirement. You can have any number of transactions running at the same time, as long as they don't interfere with each other. So a transaction only guarantees, it's not saying anything about mutual exclusion. It's saying something about success or failure. It's saying everything inside of the transaction block will either totally fail or totally succeed. So how can we have a successful transaction, two successful concurrent transactions, where they both succeed, where they're both running this code inside the transaction? Okay, let's just kind of look at a timeline. So I'm trying to check out the last two copies of Harry Potter. That was serial 1001 and 1002. So say 1001 is the session on the left and 1002 is the one on the right. Session 1 starts a transaction. Session 2 can then start a transaction. This is already the problem. This is not a mutex. If this is a mutex, session 2 would not be able to acquire the lock. Okay, now they can both proceed. They can both do any kind of selects they want and get the number of books available. Then let's say session 1 checks its count, followed by an insert. Session 2 checks its count, but that insert from session 1 had no effect on session 2. They are isolated. So it checks its count, it's fine, does its own insert, and then they both commit. The problem is this commit, the insert did not happen. The insert was isolated until the commits happen. And even then, if this commit happens within the duration of another transaction, it may not even affect the other transaction. You can change the way that isolation is handled. But by default, these two things are not going to interfere with each other in any way. It's as if they both run with no synchronization. Okay, so transaction 1 completely succeeds. Transaction 2 completely succeeds. No problem. So the transaction does not provide mutual exclusion. It does provide some synchronization if needed, but it's not a lock. Don't try to use it like a lock. Okay, so a couple examples. We've already seen some basic things like this. Session 1 can change some data. Session 2 can read some data inside of concurrent transactions. No problem. They both run. Session 1 can insert into titles. Session 2 can insert into patrons. They both run, no problem. In fact, they could even insert into the same table, like we saw, as long as they're not inserting into conflicting rows. Okay, here's a question though. What about this? So if they both try to insert into patrons, where card num is the primary key, so they're both trying to insert a primary key of 1. This is what we saw. This is where synchronization is required, and one of these transactions has to fail, and will. One of them will succeed, the other will be automatically rolled back. So I only have actually one insert in here. So we don't even really need the start transaction and commit. But if there are any number of other commands before these inserts, then one of them will roll back anything that it did before that, as soon as this conflicting write happens. Okay, so back to this question of how do we handle concurrency between clients in a web server. Well, it turns out all we really need to do to solve this problem, like check number of copies available, if it's enough, then check out the book. All we actually need to do there is this software lock in C#. I could just put a lock around my entire controller. Lock, check out book, unlock. And then since the web server is running on one machine, if any two threads running on that machine, as long as they have access to this lock, then that will provide mutual exclusion between the Joe client and the Dan client or whatever. We don't even have to get transactions involved. We can just use a C# lock. But here's a more accurate picture of a real web server, a distributed web server. Say you have some server on the West Coast, some server on the East Coast, but they're both potentially using the same database server. So different web servers, different machines, communicating with the same database machine. And you have multiple clients connected to each of those web servers. Now if you try to do this, software lock on each of these are totally different machines, totally different processes. There's no mutual exclusion between the two. It will prevent races between any clients connected to that one server, but it will not prevent races between clients connected to some other server on the other side of the country. So what we need is we need to somehow move the locking functionality to the common point, to the database. But that's not a transaction. That's a lock. That says lock and unlock. That doesn't say start and commit. So different things there. But let's look at transactions a little more. So I've said that everything we're doing with transactions is the default behavior. Turns out you can actually change the default behavior. And it comes down to the I part in isolation. How isolated do we want a transaction to be? And it all comes down to do they interfere with each other or not? And what is the definition of interference? We can specify this in SQL, and there are 4 levels. So they're called different isolation levels. I can be either very restrictive or very open. So read uncommitted, read committed, repeatable read, serializable. The names they kind of relate to specifically what phenomena do they allow to happen. But basically these are level 0 through level 3 in terms of less restrictive and more restrictive. And not surprisingly, being less restrictive is faster. You don't have to acquire any locks. You don't have to do any kind of synchronization. You just let things happen. And being very restrictive is slow. By default, the MySQL server that we use starts with repeatable read isolation level. So it's actually, second from most restrictive isolation level by default. Okay, so what do these mean though, and how can they help us with this synchronization problem between multiple clients? Here's read uncommitted. It basically means that other sessions can see what's going on even if it's inside of a transaction. So we didn't see this by default. But if I had a transaction in session 1 and another transaction in session 2, even though it's inside a transaction, if session 1 does some changes, then session 2 can actually see them, even before the commit. So this is not the default, and this is not what we saw, but we could make it behave this way. Okay, here's an interesting problem with this, though. So notice session 1 is doing a rollback instead of a commit. So session 2 could see the 1 that got inserted into table X, even though it's not actually real data. It's an inconsistent read. It would see some non-existent thing because there's no isolation level. It's just like let everything happen whenever it wants to happen. Okay. The next level is read committed, which, as the name suggests, only lets outside transactions see changes once they have been committed. So session 1 starts a transaction, does an insert. Session 2 starts a transaction. And look at the timeline here. So going down is going forward in time. Session 2 does its select after session 1's insert, but it still sees 0 rows. So that's unlike this, where session 1 did a select after, session 2 did a select after an insert, and it saw the insert. Here, with isolation level read committed, it will not see that until session 1 commits. So notice these two selects here, exact same select statement in session 2. First it returns 0, then it returns 1. Even inside of the transaction. This is all inside of a start commit block. But since the commit happened there in some other transaction, now it can see the difference. And this right here, these two selects, returning different values. That's a phenomenon called a non-repeatable read. If the exact same select statement returns 2 different values from within a transaction, that's a non-repeatable read. And that can be a big problem. If you're okay with non-repeatable reads, then read committed is, and read uncommitted is a fine isolation level. Okay, the next one is called repeatable read, and its exact purpose is to prevent that problem. It basically, each transaction operates inside of a snapshot. When you start the transaction, it makes a snapshot, and everything you do, including select and insert, will be based on the original snapshot. So even though session 1 has committed, session 2 doesn't see it until it commits, until it finishes its transaction. So look at these first 2 selects now. Inside the transaction, they are repeatable. They will both return 0 rows. So it's solved the non-repeatable read problem. Okay? But still, none of these, up until this point, have done anything about the, well, what if two sessions read the old data at the same time and then proceed based on some if statement? So the final one, and the most, the strongest isolation level is serializable. It basically means that it gives complete isolation to a transaction. So it's as though nothing else is happening. And the way that it achieves this is a select inside of one transaction can stall an insert inside of another transaction, and vice versa. So the way we've seen all of this stuff, these selects can never stall another transaction. With isolation level serializable, a select can stall another transaction. So let's look at that. This is the first case is where an insert is stalling a select. So session 1 does an insert, and then a bunch of other stuff, and then at some later point commits. Session 2 tries to select from table X that had some data changed. Instead of immediately returning either the old data or the new data, it will just stall. So this is unlike any of the other isolation levels where none of them were causing stalls. They were just either picking old or new data. This is actually causing a stall, and then as soon as session 1 commits, the select will complete. So you're guaranteed that that select will get the updated value if some other session, some other transaction has changed it. Okay, here's kind of the other way around. It's the same sequence of statements, but let's say that session 2 runs a little faster, so the select happens first. And it's going to get 0 rows. So it needs to know that it can rely on there actually being 0 rows. Which means if session 1 tries to insert, the insert is stalled, because session 2 needs for there to be 0 rows while its transaction is running. So the insert is stalled, and then as soon as session 2 commits, then the insert can proceed. But that, essentially what this does is guarantees that whatever session 2 saw was totally isolated and consistent with its own view of the world. Okay, now here's where it starts to look more like an actual mutex that might solve the problem. Still not a mutex, but we'll kind of see the difference. Question first.
So would the insert fail if session 2 did something?
Yes, exactly. So very next slide here. So let's say after doing some select, session 2 decides, maybe based on the result of that select, maybe it decides to do an insert. It needs for that to be atomic. If it selected something and got 0 rows, then decided to do an insert based on that, you need that to be atomic. Which is why, if this insert happens here, then the other insert that is waiting, as soon as that insert happens, then the other transaction will fail. So this is kind of how we can actually get session 2 read something, check some condition based on that, do something based on the condition, and you're guaranteed nothing else has changed anything or interrupted that sequence. Yeah?
Is it possible to deadlock these things?
Is it possible to deadlock? Absolutely, yes. Good news is MySQL detects deadlock. It's not just going to let both of your sessions sit there forever. It will detect deadlock, pick one of them to succeed, and roll back the other one, and report to the user that deadlock was detected and your transaction failed. Okay, so now we can kind of finally, we can rely on the fact that if I successfully selected some data out of a table, everything I do based on that data or my own insertions to that data will be consistent with a single threaded view of the world until I commit. Then a lot of other things might change. So this almost kind of gives us a mutex. It's still not a mutex in that 2 transactions can operate at the same time as long as they are not reading or writing in ways that interfere with each other. So it still is not actually a mutex lock, but it can give us the same, some of the same benefits. So let's just look here a little bit. In the MySQL command line, so the default is repeatable read. You can actually check that with this special variable, select @ tx isolation. So it says repeatable read. I can change that. I can do set for the whole session. Transaction isolation level. And let's do read uncommitted. Did I spell something wrong? There we go. So remember, read uncommitted is the least restrictive isolation level. So I'm going to set that in both of my sessions. Okay. Now let's start a transaction over here. Well, let me make sure I didn't have any still running first. Okay. Let me read that variable again. Okay, so I've changed the isolation level to read uncommitted. Let me start a transaction in both. And I will do insert into simple values, I don't know, a 3. Okay. If I select from here, I have 1, 2, and 3. If I select from here, I have 1, 2, and 3. And then if I roll back, and then go back and select from here, turns out that 3 was basically an incorrect read. It was never actually there. Okay. Let me go all the way up to serializable. And just double check. Okay. Let me see what's in the table. Okay, so we rolled back the insert of 3, so now we have just 1 and 2. Start a transaction in both. Let's do a select in both. So even with the highest isolation level, it's still letting me select from both at the same time. Now let me roll those back just to start fresh. Okay, start a couple of new transactions. Over in this one, let me do an insert. I'll just use the old command. Okay, so we'll try to insert a 3. It says, fine, you've inserted a 3. If I do a select over here, my select now stalls, because it knows that whatever I select is, we don't know what it's going to be yet. It's not permanent yet. And then as soon as I either commit or roll back, now the select can proceed and get its 3. Okay? Yeah.
Do all the sessions have to agree on what the
Do all the sessions have to agree on the isolation level? No. It only affects the one session you're working in. But, so if one session has a really low isolation level and it's running a transaction and does an insert, and the other one has serializable, serializable will still respect, like, if something was inserted in one, it will block the read in the other.
So I'm kind of confused because on your slides in session 2 you had a select happen, and that's when you said that you can guarantee from that point on the world state will be unchanged.
Yes.
Uh,
So I just did it kind of the other way around, where I did the insert before the select.
Sure. But in your first example, you had session 2 select, and then session 1 was able to select without a lock. Is that just because it knows that 2 selects doesn't change the state?
Right. So I was able to do 2 selects because none of them had done any inserts yet.
Okay.
So it knows that the state is still read only. Nothing has changed. So both the selects can proceed. But, so I did the select before, sorry, I did the insert before the select. Let's do it the other way around. So start some new transactions. Over here, I will now select star from simple. And over here, let me try to insert something. Now my insert stalls. That's actually more important than, well, they're both important. This is kind of more along what's getting us to appear more like a mutex. If one of these sessions has selected something, it needs to know that this is the state of the table until it either commits or rolls back. So as soon as I commit, now this insert can proceed because this transaction is done doing whatever it needs to do. Okay. Yeah.
So from C#, could you change your isolation level based on your current needs for what the queries you're about to use?
Yes. So that's actually kind of just goes right to the next point. So we saw that this transaction did not solve the problem at all, and it's because it was using repeatable read isolation level. When I'm creating my transaction up here, turns out I actually have it commented out. I just need to specify when creating the transaction, I want serializable isolation level. So let me go back to the library and delete all the checked out books. Let's run the web server. So what happened there? I thought I deleted from. Oh, I was inside of a transaction. There we go. Forgot to finish off that other transaction. Okay, so let's try this again. Try to check out one book in one and the other in the other. And it did not let me check out the other book. Okay, so no surprise there. That's what we expected to happen. But there's another important thing I want to point out about this. I'll just close that. So this is not a mutex. This is a transaction. What's happening is the second client that fails to check out the book, it's not failing here. It's not actually seeing that available is less than or equal to 1 and failing here. Well, it might be, but we can't guarantee it. It's also possible that it is failing right here because some other transaction has already modified this database. So the way that this code is written, just be aware, this is not the only point of return where we tried to check out the last copy of a book. So you just have to kind of write your code in such a way that it's aware of that. Which means the transaction might even fail if there are like 7 books left. It might fail due to the transactions interfering with each other. So even if there are 7 books left, you still want both of them to be able to check out a copy. So you have to detect that and restart the transaction in the one that failed until you do get to this point where the condition is met. So it doesn't really map from transaction to C# conditions directly that way because it's not a mutex.
Does LINQ directly support like retry strategies, or do you have to do that?
Does LINQ support retry? No, you would have to kind of put this whole thing in a loop and just do it again.
If we move the if statement into SQL instead, would that help us?
If you move the if statement into SQL instead, so it turns out you can't actually use a where clause on an insert clause. So there are other like less standard ways to kind of do that, but SQL by default does not support insert into whatever where condition. So we have to do the condition in, we don't have to, but we're doing the condition in C#. Does that answer your question? So there are kind of if statements in SQL. Whether or not they are supported by whatever server you're running on is a different question. Yeah. So do stored procedures interact with this? You can use a transaction inside of a stored procedure. And that is often useful, but a stored procedure is not like automatically just a transaction. If you have a bunch of commands inside a stored procedure and you don't run it inside of a transaction, then it'll just be a bunch of individual transactions. Did you have a question?
Yeah. So you said that return JSON statement right there may not be the only like exit point for this transaction. So what does it look like when it's exiting prior to that? Like when it's exiting on the save changes, for example, is that an exception?
It's an exception. So the other place where it would exit is here inside this catch block. So I'm just saying return success equals false. Either way, it's reporting to the view, to the web server, that you were unable to check out the book. Okay, that is it for today. See you next time.